Right now, at this very moment, something is passing through our solar system, and it might be carrying life. Not a robot, not a radio signal, not some distant blinking light in a telescope. Actual living organisms, microscopic passengers that could have been placed there billions of years ago by an intelligence so advanced, we cannot even begin to comprehend its scale. If that sentence made your pulse quicken, good, because what you're about to learn is not a theory pulled from a science fiction novel. It is based on real telescope data, real scientific research, and real questions being asked by some of the most respected astrophysicists on this planet right now. The object at the center of all this is called 3I Atlas, the third confirmed interstellar visitor ever detected passing through our solar system. And what scientists have found in its chemical trail has forced an entirely new kind of question into the mainstream of astrophysics. Not just, is there life out there, but something far more unsettling. Could this object be a deliberate cosmic vessel? A gardening ship engineered to spread life across the galaxy? And if it was built with that purpose, who built it? To understand why this question is being asked at all, we need to start somewhere unexpected. We need to start with you specifically, with where you actually came from. Because the story of 3I Atlas begins with one of the most startling scientific possibilities of the last century. A possibility that fundamentally challenges our understanding of life itself. You might be a Martian. That is not a metaphor. That is a serious scientific hypothesis supported by physical evidence we have already recovered from our own planet. Here is what we know. Mars is a smaller planet than Earth, which means it has a larger surface-to-volume ratio. A larger ratio means it loses heat faster. While Earth was still a molten, violent, utterly uninhabitable hellscape around 4.2 billion years ago, Mars may have already cooled enough to hold liquid water, maintain stable temperatures, and support the basic chemical conditions that life requires. In other words, Mars may have been ready for biology hundreds of millions of years before Earth was. And then the asteroids came. Massive impacts slammed into the Martian surface with enough force to launch rocks straight into space. Some of those rocks, after drifting through the void, eventually fell toward Earth. We know this is not speculation because we have found Martian meteorites right here on our planet. One of the most studied is called ALH 84001. When scientists analyzed it carefully, they discovered something that should make you pause. Throughout its entire journey from Mars to Earth, this rock was never heated above 40 degrees Celsius. That is roughly human body temperature. That is cool enough for microbes to survive. Let that land for a moment. We have a physical rock, recovered from Earth, confirmed to be from Mars, that traveled through space without ever getting hot enough to sterilize its interior. That is not a model. That is not a computer simulation. That is a specimen sitting in a laboratory, proving that the transfer of life between planets is physically possible. Now layer that onto one more fact. When scientists analyzed the genomes of 700 modern microbes to trace back to our last universal common ancestor, they found that the original life form on Earth existed approximately 4.2 billion years ago. That is only a few hundred million years after Earth even formed. For life to have emerged from raw chemistry in such a short window seems almost impossibly fast. But the timing matches perfectly with the period when Martian rocks were being delivered to our planet. Whether that is coincidence or cosmic connection is exactly the kind of question 3I Atlas is now forcing scientists to revisit with brand new tools and brand new urgency. So we have established that life can travel between planets on rocks, and that the timing of life's appearance on Earth lines up suspiciously well with the delivery of Martian material. But scientists did not stop there. Because if life can hitch a ride on rocks between neighboring planets in the same solar system, a far bolder question immediately follows. Could life travel between star systems? Could microorganisms survive not millions but billions of years in the cold, dark, radiation-soaked void of interstellar space? The scientific community has a name for this idea. It is called Panspermia, the hypothesis that life can spread naturally through space, carried on debris, flung out by collisions or volcanic explosions. And while it sounds like the plot of a science fiction film, the underlying physics is solid. Microbes are extraordinarily resilient. Certain species can survive the vacuum of space. Others can endure intense radiation doses that would kill a human within minutes. Some enter states of suspended animation, shutting down all metabolic activity and waiting indefinitely for conditions to improve. We have revived microbes from million-year-old salt crystals right here on Earth. The biological machinery for surviving extreme dormancy already exists in nature. But here is the problem with natural panspermia: it is monumentally inefficient. When rocks get blasted off a planet's surface, most of them drift through space forever, never finding another world to land on. The ones that do reach another planet often burn through the atmosphere at the wrong angle or crash into oceans with enough force to destroy anything inside. The odds of natural panspermia successfully delivering life to a new world are extraordinarily low. It can happen, but it is slow, random, and wasteful on a cosmic scale. Now ask yourself the next logical question. If natural panspermia works even barely, what would happen if an intelligent civilization decided to take control of the process? What if they stopped leaving it to chance and engineered it deliberately? What if they built cosmic vessels specifically designed to carry life across interstellar distances and deposit it on worlds with the right conditions? This concept is called directed panspermia, and it was not invented by an internet blogger or a fringe theorist. It was seriously proposed by Francis Crick, the same Francis Crick who co-discovered the double helix structure of DNA, one of the most important scientific achievements in human history. Crick looked at the chemistry of life and saw something that troubled him. The genetic code seemed almost too elegant, too universally consistent across all of Earth's life forms. He suggested that this consistency might reflect a single origin, and that origin might not have been here. Most scientists dismissed the idea as unprovable, and it faded from mainstream discussion. But then came 3I Atlas. And with it came data from the James Webb Space Telescope and the SPHEREx Space Observatory that has reignited the conversation in a way no one expected. When those instruments turned toward this interstellar object, they were looking for the standard chemical fingerprint of a comet. What they found was something that raises far more questions than it answers. The plume of gas and dust surrounding 3I Atlas contains water, carbon dioxide, carbon monoxide, and methane. Every single one of these molecules plays a role in the metabolic processes of life on Earth. Every single one can be consumed or produced by terrestrial organisms. Now, these molecules are not uncommon in space. They form naturally in molecular clouds and get locked into comets during planetary formation. By themselves, they do not prove anything extraordinary. But there is one anomaly buried in this data that is keeping astrophysicists awake at night, and it has to do specifically with the methane. This is where the story shifts from fascinating to genuinely bewildering. Methane was not detected coming from 3I Atlas before it reached its closest point to the Sun. Before perihelion, when this interstellar traveler was still approaching our star, telescopes found no methane signal at all. Zero. Then, after the object passed closest to the Sun and began receiving its maximum warmth, methane appeared. Why does that matter? Because of something called sublimation temperature. Methane is what scientists classify as hypervolatile, meaning it evaporates at far lower temperatures than most other compounds locked inside a comet. If methane ice existed near the surface of 3I Atlas, it should have been releasing well before the object got close to our Sun, not after. The fact that methane appeared late, only after significant heat had time to penetrate deeper into the object's interior, suggests the methane was buried, protected, hidden. But here is where the mystery deepens into something genuinely strange. Carbon monoxide was detected before perihelion, during the early observation campaign. Carbon monoxide is actually more volatile than methane. It evaporates at even lower temperatures. So why did we detect the more volatile compound early, and the less volatile one late? The chemistry is inverted. The pattern does not match any standard model for how a comet should behave. It is as if the interior of this object has a structure or a composition that breaks all the rules we have written based on studying comets within our own solar system. When one of the world's leading astrophysicists publicly raised the question of whether this methane could be biological in origin, it sent a ripple through the scientific community. Because on Earth, one of the primary producers of methane is life itself. Microorganisms called methanogens release methane as a byproduct of their metabolism. Decomposing organic material produces methane. Entire ecosystems generate it continuously. The connection between life and methane on this planet is not subtle, it is fundamental. So, consider what the data is actually describing. An interstellar object approaches our Sun. As warmth slowly penetrates deeper into its interior, something begins releasing methane at a rate and in a pattern that does not match geological models. What if that warmth did not just heat ice? What if it woke something up? What if organisms that had been frozen in suspended animation for billions of years, dormant throughout the long dark journey between stars, suddenly found themselves in warmth again? What if they began to metabolize? What if the methane we are detecting is not geology but biology? We do not have proof. Let that be absolutely clear. What we have is an anomaly, a pattern in the data that existing models struggle to explain. But in science, anomalies are not footnotes, they are doors. Every major discovery in the history of this field began as something that did not fit the expected pattern. And this anomaly is significant enough that serious scientists at serious institutions are taking it seriously. There is also a second possibility that some researchers find even more compelling than dormant alien microbes drifting in by accident. What if the 3I Atlas was not carrying life randomly? What if it was designed to carry life? What if this object is not a comet but a cosmic seed pod, an engineered vessel launched by an ancient civilization with the specific purpose of spreading biology throughout the galaxy? The methane anomaly, the buried organic material, the chemistry that defies standard models, what if all of it looks strange because it was not made by nature? What if it was made by someone? To understand why the idea of a deliberately engineered interstellar vessel is not as outrageous as it sounds, try this thought experiment. Imagine your civilization has mastered interstellar travel. You have explored the nearby region of the galaxy and found dozens of planets with liquid water, the right atmospheric chemistry, and conditions that could support life. But no life has started there yet. Barren worlds, each one a blank canvas. What would you do? Would you move on and leave them empty? Or would you plant seeds? Throughout all of human history, we have been driven by the need to leave something behind. We have children to carry our genetic legacy. We build pyramids, cathedrals, and cities to outlast our individual lives. We create art and literature to carry our ideas forward through centuries. Every civilization that has ever existed has found ways to say, we were here, and we mattered. But all of those monuments are local. All of them will eventually be consumed by the same fate as the planet that produced them. Now imagine thinking bigger. Not building a monument on one world, but seeding life across an entire galaxy. Your legacy would not be stone or steel. It would be entire ecosystems, entire evolutionary trees, perhaps entire civilizations that arose billions of years after you launched them on their journey. Entire branches of the tree of life, carrying the faint genetic echo of your home world across the cosmos. This is the concept of directed panspermia taken to its most ambitious scale. And here is the remarkable part. We could do this right now. With current technology, 3I Atlas is in our solar system at this very moment. If space agencies had launched an interceptor spacecraft within weeks of the object's discovery in July, that craft could have reached a crossing trajectory before the object's closest approach to Earth in December. We could have deposited a capsule containing hardy terrestrial microbes onto the surface or into the interior of this interstellar visitor. We could have included a radioactive heat source inside the capsule, providing warmth for the organisms through nuclear decay, keeping them alive and metabolizing during the billions of years journey to another star system. And then we could have watched 3I Atlas carry Earth life outward at 60 kilometers per second, more than twice the speed of any spacecraft humanity has ever launched. The estimated cost for such a mission is under $4 billion. That is roughly the construction cost of a single major skyscraper. For the price of one building, we could ensure that Earth life reaches other star systems. We could launch the longest-lived legacy in the history of our species, one that would outlast every monument ever built, outlast the civilization that built it, and potentially outlast the planet itself. The Sun has approximately 7.6 billion years left before it expands into a red giant and swallows the inner planets. Everything on Earth will eventually be gone. Every city, every record, every trace of human existence. But life seeded on an interstellar object would not be bound by that timeline. It could continue evolving and spreading for trillions of years across countless star systems. Now here is the question that makes this entire topic land with its full weight. If we can conceive of doing this with our current level of technology, how many civilizations that came before us might have already done it? The universe is 13.8 billion years old. Our sun formed only 4.6 billion years ago. There could have been civilizations that rose and fell before our solar system even existed. They had billions of additional years to develop technology, billions of years to spread their seeds across the galaxy. If even one of those civilizations chose to become a cosmic gardener, their work might have been spreading through the Milky Way long before Earth was a molten rock. Right now, as you listen to this, telescopes around the world are locked onto 3I Atlas. Every major observatory is collecting data. Every spectrograph is analyzing the light streaming off this object as it races back toward interstellar space. And they are all searching for the same thing: signatures that could distinguish biological activity from purely geological processes. The scientific strategy being deployed involves three main approaches, and each one is more ingenious than the last. The first approach targets molecular signatures. Beyond water, carbon dioxide, and methane, life produces an enormous range of complex molecules. Amino acids, proteins, lipids, and organic compounds that leave specific fingerprints in the infrared spectrum. The James Webb Space Telescope was designed with instruments sensitive enough to detect some of these molecules at extraordinary distances. The SPHEREx Observatory is simultaneously conducting a broad infrared scan of 3I Atlas, looking for patterns that do not match the baseline chemistry expected from a non-biological comet. Multiple ground-based observatories are running continuous monitoring campaigns, coordinating their schedules so the object is never out of someone's view during its passage through the inner solar system. The second approach examines isotope ratios. This technique is one of the most powerful tools planetary scientists have for distinguishing living chemistry from non-living chemistry. Living organisms selectively absorb specific isotopes of carbon, nitrogen, and sulfur during their metabolic processes. The ratio of heavy carbon to light carbon in biological material is measurably different from that same ratio in material that was never processed by a living cell. If we could obtain even a tiny sample from 3I Atlas and measure these ratios in a laboratory, we could potentially determine whether the organic molecules in its plume came from life or from purely chemical reactions. Sadly, we do not have a spacecraft positioned to collect such a sample from this particular visitor. The window has already narrowed, but the data gathered now will shape and prioritize the missions that come next. The third approach studies temporal patterns, and this may be the most intriguing method of all. If living organisms are present inside 3I Atlas, their activity should respond to temperature changes as the object moves through different thermal environments. When organisms get warmer, their metabolism accelerates. When they cool down, it slows. This creates a predictable rhythm of chemical output tied to the object's proximity to the sun. Scientists are building computational models right now to predict what purely geological outgassing should look like versus what biological outgassing would look like. And they are comparing those models against the actual observational data being collected in real time. So far, the results are inconclusive. There are anomalies in the data, patterns that do not cleanly fit the standard geological model. But there is not yet enough evidence to declare those anomalies definitively biological. The frustrating truth is that time is running out. 3. I-Atlas is traveling at 60 kilometers per second. Every single day, it moves farther from our telescopes and grows fainter in our instruments. We have perhaps a few more months of quality observation before the object becomes too distant to study at the level of detail this mystery demands. The window is closing, and the answers may not arrive before it does. What would happen if they did? What would it mean for humanity if scientists announced tomorrow that an interstellar object was carrying actual living organisms? Not just organic chemistry, not just the precursor molecules of life, but genuine biology from another star? It would be the single most transformative discovery in the entire history of our species. More consequential than fire, more significant than the wheel, more civilization-altering than the moon landing. Because it would not simply tell us that life exists somewhere else, it would tell us that life is a cosmic phenomenon, a feature of the universe itself, rather than a lucky accident on one small planet. Here is a detail that most people covering this story have missed entirely. When 3I Atlas was first detected in July 2025, scientists did not just point their telescopes at it and start collecting data, they immediately began calculating whether a spacecraft could reach it. They ran the orbital mechanics, computed the launch windows, and determined that yes, technically, if a fast-moving interceptor had launched within the first few weeks of discovery, it could have reached a crossing trajectory with the object by December. It was physically possible. We had a narrow but real opportunity to send something out there and actually touch this interstellar visitor. We did not launch. We were not ready. There was no spacecraft built, no mission architecture prepared, no institutional framework capable of responding fast enough. By the time the calculations were done and the possibility was clear, the launch window had already begun slipping away. And that is the true tragedy of 3I Atlas. Not that we could not study it, we are studying it, and the data is extraordinary. The tragedy is that we could not touch it, could not sample it, could not extract the physical material that would allow us to definitively answer whether life exists on this object. That chance is gone. 3I Atlas is on a hyperbolic trajectory, meaning it is not gravitationally bound to our solar system. It came from interstellar space, and it is returning there. Within a few years, it will be so distant that even our most powerful telescopes will lose it entirely. It will drift back into the galaxy, carrying its secrets with it forever. But here is what changes everything going forward. 3I Atlas is not unique. It is the third confirmed interstellar object to visit our solar system after Oumuamua in 2017 and Borisov in 2019. Astronomers now estimate that objects like these may pass through the inner solar system roughly once a year. We were simply not watching carefully enough to catch them before. That is about to change. The Vera C. Rubin Observatory is coming online, and it will systematically scan the entire visible sky every few nights, with unprecedented depth and sensitivity. We will find these visitors earlier, with more lead time, and with far more opportunity to prepare a response. Some scientists are already drafting proposals for what they call a rapid response mission architecture, a standing capability with spacecraft pre-built and ready to launch on short notice the moment a new interstellar object is detected. These craft would use advanced propulsion systems to chase down fast-moving targets. They would carry instruments designed specifically to analyze alien chemistry. Some proposals go further still, suggesting that we not only study these objects but use them, depositing terrestrial microbes onto their surfaces and letting them carry Earth life to other stars. Sending out our own seeds into the dark, becoming the cosmic gardeners ourselves. This is not science fiction. The technology for such a mission exists. What is missing is funding, political will, and the institutional commitment to treat interstellar science as the priority it deserves to be. But 3I Atlas is changing the conversation. The anomalies in its chemistry, the methane mystery, the possibility of biological signatures, all of it is generating the kind of scientific urgency that moves agencies to act. Plans are being drafted. Voices are getting louder. The next interstellar visitor may find us far better prepared than this one did. We may never know for certain what 3I Atlas was carrying. The mystery may remain unresolved, the anomaly unexplained, the question of life forever unanswered for this particular traveler. But the universe is not done sending visitors. And every one of them is an invitation to look harder, reach farther, and finally understand our place in the vast, living story of the cosmos. If this video made you see the universe differently, share it with someone who needs to hear it. Subscribe to stay with us as we continue tracking 3I Atlas and every interstellar mystery that follows. Drop your thoughts in the comments. Do you think 3I Atlas is carrying life? Do you think we should seed it on our own? The conversation is just beginning, and the next chapter of life in the cosmos may be written by us.